Okay, so in this video I'm going to describe Simon's algorithm, which includes a new way of setting up a quantum state, which we are going to perform Fourier sampling on, in such a way that it gives us an exponential speed up over any classical algorithm. So here's the problem that we are going to be solving. We are given a function from n bits to n bits, and we have a promise that it's a 2-to-1 function, and it's 2-to-1 in this very special way. So there's a secret string s, which is an n-bit string, such that f of x equal to f of x plus s, where plus in this funny symbol means it's bitwise sum mod 2. So for example, if n is 3 and s is 101, then we must have the case that, for example, 000 plus 101, if we do a bitwise sum, that's 101, then f of this must be equal to f of that. Or, for example, if let's do a more non-trivial example. So suppose x is 011. This was s was 101, and x bitwise sum with s is just 0110. So you just throw out all the carries when you do the summation. So here's our table for f of x. So you can see that this table has f of 011 is that, and f of 110 is also the same value. Right? This is the property that we wanted, that the function is 2-to-1. There are exactly two values of x which map to the same thing, in this case 100. And what are these two values? They are, they satisfy this relation that this is equal to this plus 101, or this is equal to this plus 101 in this bitwise sum manner. So now our challenge is to find s. So how can we do this? Well, let's first try to understand how we could do this classical. What would a classical algorithm look like? So once again, we are given this function f in the form of a circuit which computes it, and moreover, this circuit, is in the form of a black box, so we can't open up the circuit to look what's going on inside. All we can do is feed in different inputs, and so, well, we could just keep trying different inputs, but until we see two different inputs which give us the same output, we are out of luck, because there's no way we could know what s is until we see a collision. But how many x's do we have to sample before we see a collision? Well, since there are n different values, it turns out, you know that by the birthday paradox, you can actually find a collision if you sample square root n of these values at random. Which is 2 to the n over 2. But it turns out that also, in addition to the birthday paradox giving you that this is a good bound, you can do it within this number of steps, it actually turns out that you don't get, the chances that you can find a collision in much less than this number of trials is negligible. And so classically, you can do no better than 2 to the n over 2 steps. So it takes exponential time to solve this problem classically. So what we're going to see is how to use, again, this Hadamard transform, this Fourier sampling, to solve this problem using a quantum algorithm in only polynomial time, polynomial in n number of steps. Okay, so this algorithm, Simon's algorithm, works like this. So it works in 3 steps. In the first step, we set up an appropriate superposition. The superposition is going to be an equal superposition over these 2 strings, R and R plus S, where R is a random n-bit string. Okay. In the second step, we are going to do a Fourier sampling of this superposition. So remember, this is a superposition over 2 n-bit strings. You know, there's the n-bit string R, and then there's the bitwise sum of R and S, where S is what we are looking for. So it turns out that when you compute the Hadamard transform and you sample and you measure, what you see is a random n-bit string Y, where Y satisfies the linear equation y dot s is 0 mod 2. So what do I mean by that? I mean that if y equal to y1 through yn, so these are the bits of y, s is equal to s1 through s sub n, then the linear equation is that we have is that y1 s1 plus yn sn is congruent to 0 mod 2. And so now what we are going to do is we are going to repeat this process n minus 1 times. So we get n minus 1 such linear equations. Okay, so we have linear equations. Let me call this the first linear equation, and this is the n minus first linear equation. Remember, these yi's are all known, and so what you can do is you can solve these linear equations, and as long as they are full rank, they are n minus 1 equations, n unknowns, so you'll get exactly 2 solutions, since we are working mod 2, and so you'll be able to pin down all but one of the variables that takes on 2 different values. And it turns out one of the solutions will be, of course, the all zero solution, because it's a homogeneous set, and the other solution will give us what the value of s is. Okay, so that's the overall plan for the algorithm. So now what I have to show you is how to set up this initial superposition, to show that Fourier sampling will give us such a linear equation, and that if we repeat n minus 1 times, there's a very good chance that we'll get that all these n minus 1 linear equations are going to turn out to be independent, so that when we solve them, we actually get a unique solution S. Okay, so remember, as before, since we are given this function f, we can create a quantum circuit that on input x and zeros outputs x and f of x. Okay, so now how do we proceed? So what we want, okay, so we start with a set, our inputs all in the state 0. We first do a Hadamard transform on n of these input bits. So we end up in a superposition over all x of n bits of x with amplitude 1 over 2 to the n over 2. Now we feed this superposition through our circuit for computing f. And so what the output of this circuit is going to be is, in the second register, it'll contain f of x. And now we go ahead and measure this second register to see what f of x looks like. So now what does f of x look like? Well, if we were to look at this example, then we'd have a superposition over all these values, right? So the first register would contain, with amplitude 1 over square root of 8, it would contain, the first register would be 0, 0, 0, and the second register would be 0, 0, 0. With amplitude 1 over square root 8, this would be the first two registers, and so on. But now we go ahead and measure the second register. Okay, so we'll get one of these, each of these outcomes with equal probability. And suppose we happen to pick out suppose the outcome happened to be 1, 0, 0. So what's the new state of the system? Well, the answer is, in order to figure out the new state of the system, what we must do is we must cross out all the parts of the superposition which are inconsistent with this, which is these and all of these. And then what's the new state of the system? It's a superposition over this value and that value. Right? We'd get an equal superposition over this value of x and that value of x, meaning it's an equal superposition of 0, 1, 1 and 0, 1, 1 plus s. Okay, so that's the main principle. So what we see is when we do a measurement here, we'll end up seeing a superposition. We'll pick out a random value x as well as x plus s, because for both of those values, x and x plus s, we'll see the same value of f of x. Okay, so when we measure, we see f of some value r, some random number x, r, and then the first register, its state looks like 1 over square root 2 r plus 1 over square root 2 r plus s. Right? This is what we wanted. Okay, so now that we have this state 1 over square root 2 r plus 1 over square root 2 r plus s, we are going to do Fourier sampling on it, and we want to understand what the output looks like. So let's say that this output state before we measured it, is sum over all y of beta sub y. So what's beta sub y? Okay, so with what amplitude do you go from r to y? Remember, you go from r to y with amplitude -1 to the r dot y over 2 to the n over 2. Okay, but you already started with amplitude 1 over square root 2, so it's going to be 2 to the 1 over square root 2 times 2 to the n over 2, which is 2 to the n plus 1 over 2. And then with what amplitude do you go from r plus s to this? It's to y. It's -1 to the r plus s dot y divided by 2 to the n plus 1 over 2. Okay, you can further factor this out to minus 1 to the r dot y divided by 2 to the n plus 1 over 2 times 1 plus minus 1 to the s dot y. Now you have two cases. Case 1, s dot y is congruent to is equal to 1 mod 2, in which case beta sub y equal to 0. Case 2, s dot y is congruent to 0 mod 2, in which case beta sub y is what? Well, it's minus 1 to the r dot y. S dot y is 0, so this is times 2. So it's times 2 divided by 2 to the n plus 1 over 2, so it's 2 to the n minus 1 over 2. So when you sample, you see each such y with amplitude square of this, so beta sub y squared, which is the probability of seeing y, is just 1 over 2 to the n minus 1. So what's this telling us? So exactly half the y's have the property that y dot s is congruent to 0 mod 2. So out of the 2 to the n possible n-bit strings, half of them have this property, and we are sampling each one with equal probability, exactly 1 over 2 to the n minus 1. Okay, so the net effect is, after the Fourier sampling, we have a random linear equation on S. So now we want to reconstruct S. So how do we reconstruct S? So we have a random linear equation y dot S is 0 mod 2. So this is y1 s1 plus yn sn is 0 mod 2. Or it's 0 if you're working over the field of two elements. And so we can write down n minus 1 such linear equations, and we want to know what's the chance that they are not, none of these equations are dependent on the previous ones. Well, what's the chance that the first such equation is non-trivial? Well, the only way it could be trivial is if y happens to be 0. So the chance that the first equation is bad is 1 over 2 to the n. What about the second equation? What's the chance that the second equation is bad given that the first one is not? Well, the only way it can be bad is if it was the all 0 string, or if it was exactly equal to y, equal to y, the first string. Right? So let's call the, so let's say we sample y sup 1, y sup 2 through y sup n minus 1. These are n minus 1 linear equations. The chance that the second one is bad is if the second one happens to be the all 0 string or y1. There are two ways that could be, so it's 1 over 2 to the 2 over 2 to the n, which is 1 over 2 to the n minus 1. What about the third one? The third one is bad if it's a linear combination of the first two. If it's either the 0 string, or if it's y1 or y2 or y1 plus y2. So there are four ways it could be bad. So chance is 1 over 2 to the n minus 2. So on. Okay, so how many terms are there? There are n minus 1 terms. So all the way up to 1/4. You sum up this geometric series. This is the chance of being of dependency. This is the probability that we get dependent linear equations. is at most a half. Therefore, we have full rank. They are all independent with probability greater than or equal to a half. Okay, so half the time this algorithm is going to work. If it doesn't, we can rerun the algorithm. So what we're going to do is run the algorithm n-1 times, create these n-1 linear equations, solve them, get a value for s, check whether s looks good. So how do you check? What you do is you compute f of x and f of x plus s for some random value of x and check if they are equal. If they are, then you know you found the correct, try this a few times, and if you always find equality, then you know that you found the right value of s with very high probability, and you can stop. Okay, so putting it all together, this is what Simon's algorithm looks like. You start off with your input qubits in the state 0. You do a Hadamard transform. You compute f, do a Hadamard transform, and measure, and that's it. This measurement gives you a linear equation on the s that s must satisfy. Repeat this process n-1 times, collect n-1 linear equations, solve them, and you find your secret string S.